Yeah. Okay, so yeah, so we have seen a lot of stuff about large language model and foundation model. So today I'm going to talk about some of our recent work and at Google. And so mainly we work on video first foundation model, and in that we have understanding and generation two work stream. And well, we often quote this one from Feynman. So what can I create? I do not understand. So we want to look into that so that we can see whether each one will help the other or not. And so mainly I'll talk about 4 papers. Well, actually 3. I won't be able to have time to talk about the last one, but mainly I'll talk about Spare, which is one of the tokenizer that we show that we can use the frozen language model for image generation and all that. And the other one is a new tokenizer that we developed based on our prior work. And we use that for the following work, for video poet and for video prism. Okay, so the first one is Spare. So basically, again, it's about tokenizer. And we show that, okay, you don't really need to learn any codebook. You can use the codebook from language model and use that as is, and then use that for downstream vision tasks. So this kind of interesting and surprising. Okay, so again, so and this one is about tokenizer, and we show that okay, we can we make some changes based on our prior work, and then so that we add in semantics, and then we separate the encoding part into semantic and basically semantic and appearance, and we use that for several tasks. So in this work, basically, we show that, okay, once we learn the tokenizer, which I will describe in a minute, and we will be able to use in-context learning. For example, we show that if we give you 50 examples like this, an image of 0, an image of 1 or 9, whatever, and then with 50 image of that, then using a frozen language model, we will be able, with in-context learning, we will be able to answer such questions, such as an image of 1 plus 7, then we will be able to answer this. And likewise, if we show that, okay, an image of the square root of 4, then this frozen language model will be able to answer that with an image. And so what it is that is we have a tokenizer. So this one is built on top of, we use Palm V2, which is a Google language model, and the other one is ChatGPT 3.5. The Palm model is multilingual, so you will see that. So we use that to encode language semantic information. So given the image like this, then we will be able to tokenize that with different label of semantics. For example, this one will be pretzel, and then blender and coffee and so on and so forth. And so then we will be able to encode the meaning at different level. And with more layers, then we will be able to use this tokenizer with a frozen language model to reconstruct image like this. And obviously with some more layer, we will be able to generate image with greater details. And so again, so the interesting part is that we use a foreign language model, and again from ChatGPT 3.5 or Palm 2, and what we learn is that we are encoder and decoder, and basically what this shows that okay, your codebook is not that important. You can use language. In fact, there is another work that also show that, actually two. They show that they also use for the language model and use that for vision tasks, and it still works pretty well. Okay, and so what we do in this work is that we build on top of BQVAE work, and for that we added in hierarchy and also another semantic laws, such that we can learn the effective encoder and decoder. And this part is all frozen. We didn't change anything. And with that, we will be able to use in-context learning, and then we can answer a lot of questions. And for this, we obviously we do not update the model parameter. And with in-context learning, we will be able to, given several examples like this, say we take an image, we given the model with this image with text, and then with image with text, and then we will be able to answer a question like this. Okay, so and we also use that for other tasks. So we use this for image understanding for classification. And in the paper, we also have quite a few aberration study to show the number of layers and all that. And also to show that, okay, the necessity of different loss function. And for details, please refer to our paper. And we can also use this for many things for VQA. And so then if what we show is that basically without using hierarchy or without adding semantics, then language model can easily hallucinate certain answer. For example, you would a baseline model we build without semantics or hierarchy would be like this. It will answer with some nonsense sentence. And with our model, then with our encoder, then we will be able to use a foreign language model to answer different questions. And we can also use this for many other tasks. So we use this for, so in our learner world, we often use mask learning. So we mask out some part in order to learn to generate or do inpainting, outpainting, or everything. So in the CVPR paper last year, we showed that, okay, there are different ways that you can mask image or video in different way, and so that you force the model to learn that. And so here we also show that, okay, you can, and there are different ways you can do you can do different kind of masking scheme, and you will have different result. And in the paper last year, we showed that, okay, what happens is that there is two-stage masking scheme, and if you use that, you will have better result. And it's not auto-regressive, so at least in that part. So then you don't need to it doesn't take a lot of time to generate an image. And yeah, we also use that for denoising. And in the paper, we compare with many several methods. So what we show here basically is that, if you do not use the semantic enhanced encoder, then if you use some other language model for denoising, obviously it won't give you anything. I mean, this is quite this is not surprising. Okay, so again, so in this work, basically we show that, okay, yeah, you basically you can use foreign language model and with the effective encoder and decoder, and then you would be able to do a lot of stuff. And for that, and the follow-up work that we did was basically we looked into language model, and we basically treat image, video, and audio, everything as a language. And this is pure machine learning approach. And we want to convert all the signals into language sequence, and after that we can use a typical model to train a foundation model, and we also use that for downstream applications. So yeah, and so in this work in particular, we ask, okay, so we count on language model, and then so image synthesis, okay, diffusion model perform very well. So we want to see, okay, is that a true story, or is it because of data, or because of anything? So in this work, we look into that and see, okay, so head to head, would you have better result using language model or not? And we show that, okay, if you use the same training budget, same data, and you can, using language model, you still can perform very well, and you can outperform diffusion model. Of course, everybody use different data set and different model, right? So it's not easy to compare with that, but at least in this work, we use the same budget, compute budget, and same data for comparison. Okay. All right. So again, the language model have performed very well in many tasks, and then, but in image synthesis or video synthesis, we do not see that yet. So again, we want to see, okay, can we really use language model and see whether it performs well in image and video synthesis. So yeah, so here a list of work that in this domain, and so Fnac is also from Google, and it's built on our MacV2 tokenizer, and they use a different temporal model to encode video, and for all this, and then MLM is basically mask language model. So, and then some other use auto regression, as you know. Okay, so we look at all this, and then basically the key is tokenizer, and that's where we want to improve. And so, and the other thing is that we also look at language model, and then typically for language model, you have more tokens a large number of tokens. But we also want to see, okay, so in order to do that, what do we do? Because if you just simply increase number of tokens, it may not work well, which I'll show you in a minute. Okay, and then in this, we also show that, okay, when you have a large number of tokens, how would you find the right token efficiently and effectively? So so this is basically the main idea. And then in the end, we find, okay, there's one way to do tokenizer. So as you know, if you have more data and you want to use more token, right? But what we see is that simply increase the vocabulary size would not help. It would up to when you get to certain point, it will not help you. This is not surprising. This is known as a code collapse, a code book collapse. So basically, some code word or token will not be used during training, and so it will be a waste, of course. And so. And there are two tests. One is for generation, the other for reconstruction. For reconstruction, usually just need to reconstruct. So as you use more, then it will be fine. But for generation, you need to generalize that. So basically, it shows that, okay, if you simply increase the vocabulary size, it doesn't generalize that well. Okay, and again, compare with language model, they usually use a large vocabulary. And for vision task, usually the number of token or code words are usually smaller. And the other thing what we find is that usually you often find a feature space, and then the embedded space, the dimensionality is important. In order to accommodate larger vocabulary, typically you reduce the dimensionality in the latent space. And so then what's the extreme? And then over there, so you get an image, you find a corresponding latent, and then you do nearest neighbor. That's typically what people do, right? But they also require nearest neighbor search, even low in the low dimensional space, but you still have a lot of token. And so one crazy idea is that we say, okay, what if we reduce the dimensionality to 0? Basically, you don't need to search. And okay, so then we see whether it works or not. And so the main idea is this. So basically, the idea is basically you in a latent space, in a feature vector, which element you look at whether it's positive or negative. And it's positive, you put in 1. Negative, you put -1. That's it. And so in this, then you will be able to put all the token in a very sparse space. And with k dimension, lower k dimension, then you will have 2 to the k number of, you can accommodate 2 to the k tokens. And in another work from Google, we also show that, okay, it does not necessarily need to be binary. It can be multi-level. And you can also learn code work in different ways. And there are different properties. So in another paper in iClear, the other team showed that. Okay. And so what it is, again, you have a feature vector, and then you don't need to do nearest neighbor. And it's basically look at each element, and then just look at whether it's positive or negative, and then you will be able to find the token. And with that, and I'll show you how it will help. And the other thing that we do is that for image video, we change. This is CVPR, this is in Phonetic, also from Google, from another team. And what they do is that when they want to encode a video, they use 2 transformers. One is for space, the other for time. And what we find out is it performs reasonably well. But we want to see whether we can improve that or not. And so we basically adding our 3D CNN model from our prior work in CVPR 23. So we have 2 models. One is that we just use the CVPR and the MagVit. And then so basically what we do is that we encode space with 3D CNN, and then we use the temporal transformer as CVPR and see whether it works well or not. And it performs better. But then in the end, we basically just take out the 3D CNN, and then everything will be closer. We take the first frame and condition on that, and every K frame, then we learn this model for that, and it performs better. So the difference will be here. So we compare with CVPR and CVPR MagVit and MagVit2, and then we compare with these 3 models, and then basically the joint of image and video model performs better. And also, so for this tokenizer, then we will be able to increase the vocabulary from 2 to the 10 to 2 to the 18 and more. And we still can train that very effectively, and it's quite efficient. And so here are some operations for different things, and then we compare with different different loss function, all that. And for detail, please see our paper. And again, so then this tokenizer is very important. The main thing is that it allows us to increase the vocabulary size, scales up very efficiently, and also effectively. So we compare with VQ-GAN, and we use this for generation and reconstruction. And this is the tokenizer we use for the video point for the video generation. And yeah, so again, and the main thing is this tokenizer is very effective. And we use this tokenizer for analysis because you can use this for compression easily. And we compare with the state-of-the-art compressor. Okay, and so here's the main thing. So we compare with diffusion model, as I mentioned at the beginning of this part. So basically, we compare with other diffusion models and use ImageNet as data set, and we train on the same data set using similar compute budget, and then we compare with it. So here we show that, okay, yeah, if you use our MACV2 tokenizer, then we will be able to perform better, at least in terms of FID, better than a diffusion model. And visually, it also looks nicer. And again, this is the cornerstone we use for the video point, for video generation. And yeah, so this image and this video, and then again, it performs well against a diffusion model. And this MACV2 tokenizer is the main thing that we use for the follow-up work. We have one mask language model in this work, and this can also be used with diffusion model. And it's not like we don't like diffusion, or we just want to see what language model can bring you. And the other team also bring, again, use this tokenizer with latent diffusion model and use that for the generation in the WOT paper. Although we use a different kind of masking learning for imagery and video synthesis, and the other team basically use the same tokenizer and use that for autoregressive based video generation, which I'll explain in a minute. And okay, so yeah, again, this tokenizer is also used for video understanding and part of the video prism work. Okay. So yeah, so basically, in the end, I'm going to describe one work. Basically, we treat all the modality as language, and then we just convert that into sequence and see whether we can synthesize. Basically, you have left to right, and then we condition on some part of sequence and see whether you can generate signal or not. Okay, so again, the question we ask is that is video a language? And yes, maybe, I mean, but basically what we do is that, okay, and if so, then how do we use that? So in this work, basically we use all the modality, text, image, steps, and mass video, and we use that and into this model and see whether we can do any to any. So basically, with this model, we will be able to generate text, video from text or audio from text and all kind of stuff. And yeah, so again, it's not that, yeah, we basically, people often ask about diffusion and language model, and we want to see, okay, all right, so then can we use language model for this task or not? And the main thing, again, is this. So what we do is that the model is pretty simple. It's not that fancy. It's basically just a very typical language model. And what we do is that we have a different kind of tokenizer. For video, we use the MACV2 as I described a few minutes ago. And for the audio, we have another tokenizer called SoundStream from Google. And then for text, we use T5XL. This is also from Google. And basically what we do is that we convert everything into token and as a sequence. And but for different modality, we use different tokenizer. And then basically you convert into that and then convert into a sequence. And then you force the model to learn that. So, so basically, we basically insert token on the left is a sequence to sequence learning. And then you condition on previous what you have seen before and ask a model to learn later. And we also And basically we use max learning for that. And with different masking method, you will be able to learn to generate or for different vision tasks. And of course, here we deal with many tasks. We also need to have a token for different tasks. And oh yeah, I described this MacViv2 tokenizer a while ago, so I'll skip this one. And oh yeah, so this is the same thing. Okay, so the main thing is, again, for MacV2 tokenizer, what we do is this. So what we have is that we can increase we can accommodate a large number of vocabularies. And if you look at the distribution, this starts to look like language model. If you look at language model, they have a long tail because they have larger, they use more tokens. But then for video, we typically use much less, but with MacV2, we can scale up and such that we can learn more stuff. And so this answer query language is we answer that partially. We answer is a video a language, and the answer is yes. We can treat this way, and then at least the tokenizer look like that. And I'm going to show you some results soon. So yeah, so then basically so this model has 8 billion parameter, and here some data, and yeah, it takes a lot of time to learn. We use VLP. This is a Google TPU, so we use there are a lot of TPU to use, sure. And for this, then again, we use for different tasks, we just need to mask different ways. For example, for implanting, basically you just use a mask out part and ask model to learn. And for prediction, you can also do that. You can mask out some part and force the model to learn different things. And for all the tasks, you have to alternate and among them using text token, such that you tell the model the task to learn. And with this, then you can learn a lot of tasks. So we use this for video generation, text to video fish, frame prediction, and implanting, outpainting, stylization, audio to video, and all that, and video to audio. Okay, so sorry, I'll skip this one. So and just like a typical video generation, you often operate in a low resolution, and in the end, you have a super resolution module such that you can synthesize video with 512 by 512 resolution. And the funny thing is, you also see that okay, the super resolution also oftentimes can correct some artifact for you. If you train the super resolution module well, then you can correct some artifact for you, such as this one here. Okay, and so yeah, so there are a lot of details in the paper that we can tell you. Okay, so scale how we scale the model with different data and different model size. And so here are some results. So and then you can use so basically in the end we want to have any-to-any generation. So we can do this image to audio. And okay, so then with that, you can also provide different prompt for video generation. So with same if you give the model with different prompt, then you will generate different things for you. For example, here, so you have input video, and then you can provide with different prompt, and it will be able to generate a different video for you. So for long sequence, so what we do, well, this model was released in January before Sora. Okay, so what we did in this for long sequence, what we do is that we wrote down scripts. And for each segment, you can generate short video based on scripts, and then you just put them together. And so this one is the model we released in January. So
in the Amazon raccoon forest lives Rookie the raccoon and his family. Rookie loves to play soccer with his friends, collect acorns from the trees, swim in the river, and catch fish. But what he loves most is exploring new places and sniffing new smells. Except he's never made it out of the vast forest. Every night he dreams of seeing exotic places like Times Square and the Golden Gate Bridge. One day he sees a portal of yellow light, and his curiosity makes him step inside. Suddenly he's falling through a long tunnel which takes him to Paris. I've never seen anything like it, he says. And then to the Great Barrier Reef and even the South Pole, where he makes some new friends before visiting the ISS and ultimately the planet Androida, where the locals didn't speak raccoon, which makes him miss the raccoon forest and especially his family. Rookie quickly finds his way back home. He's so happy to be back with his friends, but also grateful for his adventures. I guess he's not such a rookie anymore.
So you even wonder about the temporal consistency and length. So I can briefly touch on that. So basically, one of the reasons we should use raccoon is that because they look all similar. We do not even try to generate long video with human because it's unlike we are not able to do that yet. But raccoon, they all look very similar. Okay, so that's a trick. And then the other thing, again, this one was released in January, and then we were blindsided by Sora in March. So then internally, there are still different model being developed to compete with Sora. Okay, and of course they also use different. There are a lot of speculation about how they train the model and open AI. All right. So then, yeah. So then, obviously, they use data and they even use some. It's been some people said they use YouTube video and then all that. So again, data is the key. If you can do that and with sufficient computing, you can do that. And if you talk to a lot of people working in this space, they will say it's mainly about infrastructure and data. And to some extent, it's true. And yeah, so this standardization. So then for that, the model actually is very simple. It's just sequence mask learning language model. But the question is how you scale. And surprisingly, the model is also, I mean, if you feed the model with sufficient data, then it will also do something good for you. So we just gives a different prompts such as a fast 3D 60 panoramic video camera, and then the model will be able to synthesize that for you. So yeah, the model is able to learn a lot, and then also with camera motion, you don't need to. You just need to fill with different prompt, and then it's given sufficient model and given sufficient data and good model and sufficient compute, then you can do a lot of amazing stuff. And we do a lot of evals. So for detail, please see our paper. Okay, so now use 3 minutes to describe another word that we are. Both work will appear next month in ICML. So these are two work. As I mentioned, we have video generation, video first foundation model effort. And then with that, there's generation and there's the understanding. And this part is about understanding. So with this, so video freezer is foundation model that allows us to do a lot of video tasks. So we use that for classification, localization, video to text, and other behavior monitoring tasks. So we evaluate against 33 tasks and all the benchmarks that we can find in the public. And then it outperforms 31 methods, and then tied with another one, and then perform worse than one model on one task. And so what we find out is that for video, and as you may know, for different data, they have different characteristics. So for some videos, say for kinetics, you don't really need to depend on temporal information. Just based on image, you will be able to tell what it is. And for some data set, you do need to know the motion in order to know what's inside that. And there are also some other tasks, such as AVA, where allows you to do localization. Basically, long video, you need to localize which motion appears from frame A to frame B. And so, and we find that, okay, there are several methods out there, and then some of them perform well on one data set, and some perform well on the other. They do not perform all that well on all the tasks. So this motivates us to do this work. And basically, we show that, okay, with this video prism model, you will be able to perform well on all the tasks. And so again, so there is another work that we did called video glue. So basically, it's a benchmarking. So basically, we look at all the data set we can find we also scroll all the data, benchmark data set and also the data set we can train on. Then we use that for comparison, and it's just to know what's out there. And so for this work, this basically we show that okay for image based that kinetics. So then you can do well just based on image, and for the other you have to use motion. And we just want to see what's out there and then see what we can develop. Okay, so then the key, again, not surprisingly, is data. And we find all the data set we can find in the public. And we also use some in-house data set. And we use high quality, of course, there are some, we need to find the image and video with text, the pair. It basically, the first, I will explain, in the first part, it's like clips. And basically, you have language and text pair, and then you train the model. The question again is you have to use a lot of model, and how do you get around? How do you use data efficiently? And so if you look at all the data set out there, some of the image text pair is not that precise, and this turned out to be an important problem for us to learn to train well on all the data sets. And in the paper, we describe all the details how you can use that and the distribution. So the training part is actually, again, it's not surprising. It's also quite straightforward. The first part is basically we just use the text. They just say we want to, we have image pair or sorry, we have video text pair, and we just train the best model in using a way like clips. So basically contrast learning. You just see, okay, what's in there, what's not all in here, and then do a contrast learning. And once you learn this representation model, video encoder, then we freeze it, and then we train another student model, and basically with mask learning and contrast learning to see how to distill from the teacher model, and also with different strategies such that you can train everything well. And again, the training part is not like complicated. It just, again, best model is based on script, and then here we have teacher-student model for that. And again, in the paper, you can see a different kind of operation study. I'll skip that. Okay, and then we said you can for different prompting, then you can use for downstream tasks in different ways. This is a complicated table. I won't bother you, but just to tell you that it requires a lot of extensive evaluation on all the data sets. And okay, yeah, the number. Okay, so anyways, just to show that okay, it's perform well on all the tasks, in almost all the tasks except one or two, in different way and a different number. So I'll skip this. I won't bother you with that. And I don't know why the text of scrambled. Okay. Anyway, so and for detail, please see our paper. And so the question is whether are we going to release this model or not? I think the answer is yes, but then for the generation, most likely not. But for the for this video present, I think we will release that. Okay, but for generation, we cannot do that yet. Okay, and yeah, and this video present is also used in Gemini. So you may have heard about this model. So we are now in Gemini. Well, we are now in DeepMind. So then this representation is also used in Gemini. Okay, yeah, I'll skip it. Okay, so all right, so the conclusion is, yeah, multimodal learning is interesting, and it does allow amazing stuff, and it allows you to get away with many things. And when you have a very effective foundation model, then you certainly can adapt that in different ways for downstream tasks. So with that, that's all I have.